I am pleased to introduce today's session, Building a Semantic Text Search Application, and our guest speaker, Yujin Tang. Yujin is a developer advocate here at Zillis. He has a background as a software engineer working on AutoML at Amazon. Yujin studied computer science, statistics, and neuroscience with research papers published to conferences including IEEE Big Data. He enjoys drinking bubble tea, spending time with his family, and being near water. Welcome, Yujin.
Thank you for that introduction, Emily. Thank you, everybody, for being here today. So today we're going to be talking about how you can build a semantic text search application. And this is going to be an application. This is going to be a hands-on workshop. So, you should have an IDE ready, and you should have Python 3.9 ready to go. I use VS Code, so I suggest using VS Code. Once I kind of go over the conceptual concepts, I guess, of what semantic search over text includes, we're going to dive into the code, and I will show you I will do the virtual environment, and I will do the install. So all you need is your IDE and Python 3.9. Okay, so let's get into it. Today, we're going to be talking about semantic search over text. My name is Yujin Tang. Okay. I'm a developer advocate at Zillis. You can connect with me by emailing me at yujin@zillis.com or going to my LinkedIn or my Twitter. I'm more active on LinkedIn, and that QR code there is a QR code that links to my LinkedIn. If you are on your phone, you can scan that. And then a little bit about the company Zillis. We are the maintainers of Milvus, the open source vector database, and you can follow us on Twitter at Zillis Universe. You can find us on LinkedIn at Zillis, and you can join our Slack at milvusio.slack.com, or you can check out the GitHub for Milvus, the vector database itself, at github.com/milvusio/Milvus. Okay, so today we're going to be covering 3 sections of concepts. So we're going to talk about what is semantic search, and then we're going to talk about what a vector embedding is, and then we're going to get into how you can do semantic text search. And at the end, we're going to do a demo where I'm going to, a workshop where I'm going to walk you through the code. So what is semantic search? The idea behind semantic search is semantic similarity, which is that some words are similar in their meaning. And this paper is one of the first papers in this space. And this is from Word to Vec, and this is basically showing the 4 words, queen, king, woman, and man. And the idea from showing you these vectors is that if you subtract the word woman and add the word man to queen, you should end up with this vector king. And semantic search is if we take that idea of vectors and having words as vectors and apply it to a large scale, we can find words that are similar to each other through looking at the distances between the vectors. And it's important to note that, today, the power of vector embeddings is actually much stronger than it was before. Now we have much more complex vector embeddings, and we can embed more than just words. We can do phrases, sentences, paragraphs. And so, for example, in this slide here, if we were to look if we were to do semantic search and we were to look at the word protein, we could see that the 3 closest words would be, ions, reactive, and glucose, or maybe molecule. So that leads us to vector embeddings. This is what we use to do math on our words. And the idea of a vector embedding is it is basically a set of numbers that represents the semantic meaning of your word. And this is a screenshot that I took from the Zillis Cloud website that shows you what some of the data in your vector database would look like. And I really want to direct your attention here to this title vector column. So this is a vector representation of the titles So, here are the titles you see in the column next to it. And here we have a bunch of floats. You can see that this is like, point something, 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 comma, point something, something, something. And in this case, we have 784 numbers representing a title. And in our demo, we're going to have a slightly different vector size. And the vector size is going to depend on the chosen model that you create your vector embeddings from. So how are these vector embeddings actually generated? Like I said, they're generated from a model, right? So if you have a neural network model, if you have something like this, right, you would input your words or your phrases, sentences, whatever, and you would get some sort of output. Maybe your output would be something like the part of speech or the type of entity, named entity recognition, or some sort of classification. And the way that vector embeddings are generated is we just put the words, the phrases through the model, and we go and we take the penultimate slide. We take the second to last layer, and that layer contains some numbers that represent your word. And in the example that we show here, this layer would be a layer of 784 neurons in which each one gives you some sort of number that represents your word. And some tools that you can use to generate vector embeddings include, OpenAI. OpenAI has their OpenAI embeddings. You can go to Hugging Face. This is what we're going to use in our examples today. We're going to use sentence transformers from Hugging Face, or you can use Cohere, which also has a way for you to generate embeddings. So how do you do semantic text search, right? So we know what semantic search is, we know what semantic similarity is, and we know that we can do math on words using vectors. What you first want to do in your semantic text search is you want to have some sort of knowledge base, some sort of documents. And so today we're going to be using a data set from Kaggle, and it's also available on Google Drive, and both of those links will be dropped in the chat. And then you take your data and you put it into your deep learning model, and you take your vectors from the second to last layer and you store it in Milvus or a vector database. And so for this example, we're going to be using Milvus, but there are other vector databases as well. And so before we dive into the code, I'm going to just cover a little bit about what the code is going to do. First thing we're going to do is we're going to download and import our data. And I'm just going to, oh, Emily, can you share the Colab notebook? So all of the code that you're going to see today is available in a Colab notebook, and I'm going to be walking you through most of the notebook and what it does. So the first thing we're going to do is we're going to download it and we're going to import the data. Then we're going to take a look at the data. We're going to explore the data, kind of make sure we have an understanding of what kind of data we're working with. That's always really important. And then we're going to clean the data up, just to make it usable. And then we're going to spin up a vector database using Milvus Lite. Milvus Lite is a vector database that you can use right in your Jupyter notebook. So, you don't have to install anything. It's going to be done through pip install. Then we're going to get the embeddings from the sentence transformers, and we're going to populate the database. And then we're going to query the vector database with a couple query examples. So yeah, this is what we're going to go through. And that's the last slide. I'm going to open up my IDE now. So open up my IDE. Where is it? Yes. Okay. So this is VS Code, and basically I've created a completely new environment. So if you have a workspace, you just make there some sort of name and you dive into it. So first thing we're going to do is we're going to go in here and we're going to create an IPython notebook. So I will call this semantic text search.ipynb. And then we're going to open up a virtual environment. So virtual env STS. And so I'm using, a version of Python 3, and then we're going to activate this. So source STS and activate. So now I'm in this, and I can pip install the libraries we're going to need. So I'm going to pip install PyMilvus,
Eugen,
which
sorry
is,
to interrupt. Can you bump up the text size just a little bit?
oh, yes. Yeah, I can make this look bigger. How's that?
Thank you.
Okay. So we're going to pip install PyMilvus. PyMilvus is the client that you use to interact with the Milvus database. And there's actually going to be a PyMilvus client coming soon. It's going to be released tomorrow. And then we're also going to install sentence transformers, gdown, which is how we're going to download the data set from Google Drive, and Milvus, which is Milvus Lite. Oh, and Python environments. And so we need to install ipykernel. So once this runs, we should see this installed. The next part we're going to do here is we're going to download the data set. I'm just going to copy and paste the code for this, and I'll talk you through it as the libraries are installing. So obviously we're going to start by importing gdown. This is our Google Drive downloader. And then you're going to get the URL to the Google Drive link, which should be in the chat. And you're going to tell it to output to a zip file locally. And then you're just going to download it using gdown. And then we're going to import zip file. And we're going to use our zip file to read the zip file and extract it into a folder that I call White House 2021-2022. Oh, right. So the data set that we're working with is a White House speeches data set from 2021 to 2022. And I specifically chose this data set because ChatGPT doesn't have access to it yet. And so later we're going to be building a large language model application. That's next month. And we're going to use ChatGPT in that. So first thing we're going to do is we're going to download this, and we're going to zip it, and it's going to unzip it and get the data. Now that we have this, what we want to do is we want to take a look at the data, and we want to actually clean it up. So once again, I'm just copying and pasting the code from the collab here. You have the notebook. You should be able to copy and paste and kind of follow along. We're going to use pandas for this. I think pandas is actually already installed. And if not, I'm going to install it, but it looks like it's already installed. And then we're just going to read this. We're going to read the CSV, and we're going to take a look at what it looks like. Okay, so we can see here that, we can see a title, a date time, a location, and the speech. And right off the bat, we notice that there's some issues with the speech, right? There's these NaN values, these null entries, and these are completely useless to us because they don't provide any semantic meaning. And then there's also these /r/n's, which are used to format the speech in the document, but totally useless to us. So what we're going to do here is we're going to start off by just dropping the nulls. And then we're going to take a look at our data frame. And we'll see that we don't have any nulls in the speeches anymore. And if there were any nulls in the titles, the date, time, location, they've also and we can see that we still have a little bit of an issue here where we have this time as a speech, and this is due to just error in the data. And you'll come across this kind of stuff often. So what we're going to do is we're going to clean this data up. And I'm going to call this one cleaned df, and we're going to set this equal to df.location, where the speech.strength.len, not strength.string, is greater than 50. And this just makes sure that we're going to have more than 50 characters in our speech section, so we're not just looking at some sort of time. And now we'll see that, we don't have anything that looks like just time anymore. And we'll also see that this was 1,000 rows, this was 637. So there was quite a lot of dirty data in this data. And the last thing we want to do is we want to replace and I just copied and pasted this. The last thing we want to do is we want to go, as a string, we want to replace these /r/n, these /r/n values that are completely useless to us. And then we'll just pull up what a speech looks like to make sure that we don't have any of these /r/n characters. So now we see, 6:47 p.m. The president, well, thank you very much, et cetera, et cetera. Why can't I code? Okay. And there's no /r/n's in here like there are in here. Now, if we want, so in this case, I'm just going to cover this very briefly as a data cleaning thing. And if we want to be able to filter later on, if you want to be able to filter by date time later on, what you're going to want to do is you're going to want to actually convert the date time, which right now is a string, and you're going to want to put into Unix date time. And we'll just see what that looks like. And so we'll see the Unix time has, all of these date times in numerical order, and we'll see the date times have been converted from strings into actual date times. The next thing we're going to do is we're going to actually start up the vector database, and we're going to start that by just establishing some constants that we're going to use throughout. And the reason why we establish these constants for best practice, we don't want to be changing numbers in multiple places. No magic numbers, right? So we're going to call our collection. A collection is kind of like a table. It's basically a set of data that we put into Milvus, and our collection name is going to be White House 2021-2022. And our dimension size is going to be 384. So this dimension size is actually derived from the dimension size of the sentence transformer model that we're going to use. And then we're going to have a batch size of 128. So this just means that we're going to be putting in 128 rows at a time. And so you'll see that we have 637 rows. So we're going to be doing 5 batches, basically. We're going to be doing 4 full batches of 128. That'll get us up to 512. And then we'll have one at the end of 125. And then top K is used to determine how many results we want to return from our query in our vector database. So in this case, we have 3, which means that when we query the vector database, we're going to get the top 3 results. Okay. Now what we want to do is we want to spin up Milvus. So the first thing we're going to do here is we're going to go from Milvus, import default server. And this is the Milvus Lite server that runs directly in your notebook. And then from PyMilvus, the client side, we're going to import connections, which allows us to actually connect to the server. And then we're going to import utility. And this is the utility import is mainly so that we can kind of look into what the server is doing. So it allows us to get the server version. And we're also going to use it to check if we have an existing collection and drop the collection if need be by the same name. So what I'm going to do here then is I'm going to import these, and then I'm going to start the default server. Yep, this only takes a few seconds. And so once you start the default server, you say, Milvus Lite, welcome to use Milvus, and you can check the version here. And then we will connect to it. So we'll use connections from PyMilvus, and we'll connect. And the host is going to be localhost. So it's going to be 127.0.0.1. Oh, that's, oops. Well, oh, connected. Okay. The port, we're going to pass it a port because you can also adjust the port. And, if you ever move to Zill's Cloud, you're going to need to know what the port is. So the port, we're going to do default server dot listen port. Okay. Now we can just use utility. I'm just going to show you how to use utility here. Utility.get server version, right? So we'll get the server version, and we'll see that we're using 2.2.8 Lite. And now we're going to go and we're just going to clear our collection, just in case that we have an existing collection with the same name. We don't want to use that. We want to use an entirely fresh collection. Or if you have a collection by the same name, you can just check, if utility dot has collection, by the name, then you can see if you have the collection and you don't want to drop it, then you can just check to see if this is true. But in our case, what we're going to do is, oops, that's in all caps, utility, and we're going to drop the collection. Okay. And now we're going to move into building the schema. So this is a really important part. I'm going to walk through this. And once we create the schema, I'm going to just pause for a couple minutes to see if anybody has any questions about the code that we've gone over so far. And so you still need a schema in a vector database. If you are familiar with databases, you know what a schema is. If you think back to taking computer science at college, you probably remember normalized database schemas from SQL and things like that. So you don't need to have your database in first, second, third, or fourth form normalization here. What you really need to do with the schema for a vector database is you just need to define the schema so that you have the metadata, because sometimes you want to have more information than just the vector itself. It's kind of useless if you just have like a vector and you're like, this vector is close to other vectors. Like, great, it doesn't mean anything, right? So you want to have like some information along with your vector so that what else you kind of need to do, or how you can use it, or you have some sort of context. If someone else comes along later and they want to use the database, they can kind of see some context from it. So the way we do this is we're going to start and we're going to go from Time Milvus. We're going to import 4 things. We're going to import field schema. This is what we use this is like the object to define a field in the schema. And then collection schema, which is the object that we use to define the schema for the collection. Data type, which tells us what kind of data type goes into a particular column. And then collection, which is the actual collection itself. So the first thing we're going to do is we're going to start here and we're going to make a list of fields. So the first thing we're going to need in our list is an ID, field schema. Name equals ID. And D type equals data type dot int 64 is primary equals true, and auto ID equals true. So if you're familiar with working with most SQL or NoSQL databases, you are probably familiar with the is primary and auto ID. This is basically auto increment, and this is basically saying that this is the primary key. And in this case, you don't actually, so one of the things about Milvus here is you actually don't need to, you don't actually need to have the auto ID be true. You can have your primary key be something that is not auto incremented. And then we're going to add the next part, which is going to be the title. Title. And that's going to be data type. And we're going to make it a .varchar. Max length equals 500. So I don't think there's actually going to be any 500 length character length strings here. Varchar is just the string. If you're familiar with SQL, same thing. Instead of varchar, parentheses 255 or parentheses 500, we see varchar as just our ability to define a string data type. Next, we're going to make the date. So you can also make this the Unix date if you would like, but I'm just going to make this the string max length equals 100. So this, obviously we don't have any 100 character length strings. You can make this anything that holds the number of characters in an expected string length and the expected date length. Sorry. Now we'll do field schema again, and we'll do location. And this is the location that we saw earlier, right? Like location not determined, or the Eisenhower Executive Building, Princeton, New Jersey, something like that, right? So this D type is going to once again be a varchar. Okay. And this is going to be a max length of, we'll just say 200. And then finally, we're going to make the field schema with the embedding. So this is going to be the embedding. and d type equals data type dot float vector. Oops, float vector. There it is. And this is going to be of dimension. And so this is going to be our embedding of the actual text of the speech itself. And yeah, this is how we create the fields for our schema. And then we create the actual schema by setting the schema by wrapping collections, collection schema over these fields that we just, created. And then we create the collection by having the collection equal to a collection that's with the name of our collection that we defined earlier and with the schema that we just defined.
Eugen,
Okay,
we've got a
so
couple of questions from the audience. Is it data or date?
which one? This one. Yes, this should be date. Yes, good catch. Okay, that was a typo. Are there any other questions about the code right now?
No, I think we're okay. We've got some for the end, but I think we just had a couple people ask about that.
Okay, yes, thank you. That was a good catch. I did that on purpose to see if you were paying attention. Okay, so the next thing we're going to do is we're going to define the index. And the index is really important because this is how you actually query the vector, basically. So the first thing we're going to do is we're going to define our index parameters. And this is going to be a dictionary. So index type is going to be IVF flat. Oops, IVF flat. Metric type L2 and params. I'm going to explain this in a second, but and list. Okay. So for this, what we're defining here is the index type, which in this case is IVF flat, and this determines how we actually create and query the index. And so IVF flat means that we're going to use the inverted file index, which is just one way that you can create a vector index. You can use other indexes such as HNSW, which if you join the Slack, you'll get a link to that in my welcome message. There are what else there's like annoy. There's just straight brute force. But this is like a very basic index type that's pretty much used for anything that's simple enough and not something that you need to do at scale, but also provides nice latency. The metric type of L2 is the L2 norm for the vectors. The other metric type that we provide is IP, and that's basically your cosine similarity. And then enlist just means the number of, we're looking at basically 128 centroids. Now we're going to, collection.create index, and we're going to give it the field name, embedding, index params equals index params, and then we're going to load the collection. Okay, here we've just finished creating our index, and I'll pause here to see if there's any questions about this index type.
There are. Do you want me to read them out to you, or are you on top of it?
I just opened the thing. How do you decide if we should pick IVF flat but not IVF SQ8 or HNSW? The best index is, so I just pick IVF flat here because it's easy. Like you can do the scalar quantization, or you can do, hierarchical navigable small worlds. It is up to you. These have, so for example, scalar quantization, you're going to have a smaller index, but it's going to be not as accurate, or HNSW is going to be, it's going to be more memory, but it's more accurate. So it's up to you on how you want to do that. Do you always prefer L2 to cosine similarity? No, that is also up to you depending on what you need. What does load do? It loads the collection so that we can use it basically. If you want a more technical deep dive into what exactly load does, I would just read the function on GitHub. Okay. Now we're going to get the vector embeddings and actually populate the database. So we pip installed sentence transformers earlier, and now we're going to load that up. That's the model from Hugging Face. So from sentence transformers, import sentence transformer. And we're going to create our transformer. This is going to be sentence transformer. And I'm just going to pick this one. It says all mini LM L6 V2. There is no specific reason why I'm picking this other than it is a popular one to use and it works well for general purpose use. There are many available embeddings and you can use basically any one that you want. This is a very popular one to use. OpenAI also has one. But yes, that's just why I'm picking this. Okay, I see there's a couple questions. What do you think of the GUI? I'll answer that later. Seems like you need people familiar with linguistics. You don't need to be familiar with linguistics. I think that is, you can have somebody for that, but we can also address that towards the end. I'm only going to take questions about the code for now, okay? Okay, so now what we're going to do is we're going to create a function that's going to embed and insert our data all at once. Okay, so this function does two things. It takes the data, the raw data, it turns it into a vector embedding, and then it inserts it into the collection. Embed, insert data. And we're going to create our embeddings from our transformer. Dot code data 3. And so I just want to note here that I'm creating this function with the idea of how we're going to insert this data in mind. So data 3 is going to be the fourth entry into a list of lists, and that's going to be the text of the speech. And you'll see that we create that list of lists later. So this is kind of, you need to create this function with the second function in mind, and we're actually going to be changing this up with the Milvus client. It's going to be easier to do. You can do it more intuitively, but this is how it works at the moment. And so I will take questions after I do the next section as well. So the insert, we're going to do data 0, oops, data 1, data 2, and then for X and embeddings. So this is basically vector for vector, the vector and embeddings, and then we're going to call collection, and we're going to insert our list. So now we need to create the data batch. So in this case, we're going to create a list of lists. So it's going to be a list of 4 lists because we have 4 data types. We have the title, the date, the location, and the speech. And we're going to create a list of lists because we're batch inserting at 128 of them at a time. So data batch equals and then for the title, the dates, the location, the speech, and zip means df dot location title. This one should be date time. This one should be, what did I say this one was supposed to be? Location. This one's going to be the speech itself. And then we're going to just append all of these separate values into our list of lists. Data batch 0 dot append title. Data batch 1 dot append as a string the date. I wrote data again. Wow. Okay. Clearly, I like to write the word data more than I like to write the word dates. Data batch 3 dot append speech. Okay. So then if the length of any of our data is in our data batch, so 0 is dividable by the batch size and equals 0, we will say embed data batch, and then we'll reset data batch to equal an empty list of lists. And also, you can also just check if it's equal to the batch size, but this is kind of the standard in machine learning. It's just how people usually write it. Then at the end, if our data batch is not empty, then we want to insert the unempty data. And we're going to call flush to index and load all of the data points. So actually what I'm going to do is I'm going to, actually we'll just call it in the same block. Okay, so this should take about 20 seconds, 30 seconds. What is the best way to insert data in index, or first index data and then index? I'm not sure I understand your question. Yeah, maybe you can clarify later. But generally, you insert your data and then create the index, and you can continue to insert your data and update your index as you need. So one of the nice things about Milvus is that everything is done in 512 megabyte chunks, so you never really need to reindex. You can just continue inserting your data. You can upsert, you can delete, and it kind of, you don't need to reindex because everything gets queried in parallel and it's fast enough because the data size is small enough. And I'm not sure what the question is, but we're going to move on and we're going to just do the querying now. So this is the last part here. What we're going to do is we're going to create some code to query our existing database. So this import is unnecessary. I'm just importing the time to show you how long this takes, just to demonstrate how quickly this is done with IBF flat, which is not even the fastest way to do things. Search terms, and so I'm just actually going to copy these because this is not terribly important. Okay, I'm going to be searching for the president speaks about the impact of renewable energy at the National Renewable Energy Lab, and the vice president and the prime minister of Canada both speak. So just keep that in mind for what we're searching for. We'll see words that are similar to those appearing in the speech, and the titles will return, the query will return will be speeches that are similar to the words that I just queried for. So now we need to create a function called embed search. And this will embed the data using sentence transformers and then search for it. So the first thing we're going to do is we're going to create the embeddings, which we use a transformer to encode the data, and then we're going to return a list of lists, or a list of, is this wrong? We're going to return a list of embeddings. Now I'm going to this will tell us when we start our query, and then at the end we'll have an end for when we end our query. So the first thing we'll do is we'll create our results and we'll do collection.search. And now this is how you actually query the data. So the data that we're going to search for is in search data. I need to create a search data, sorry. Search data equals embeds search terms. Okay, so the data is going to be equal to search data we just made, and then the fields that we're going to be looking for, the approximate nearest neighbor field is embeddings. Embedding. And then the parameter is going to be L2 metric type L2, and we're just going to look into the 10 top centroids for IVF, and so that's in probe 10. Okay, cool. And then after this, we're going to get the limit of top K. So this means we're only going to get the 3 top the three top results, and then output fields equals, we're just going to look for the title. Oops, title, there you go. And that will give us our results. And then we're going to loop through the results that we got. Enumerate results. So we're only looking at 2, and we're going to print out the search term. I call this title in the Colab notebook, but you know, you can really call this whatever you want. It's just the search term. Actually, this kind of probably goes to the end. Search time. And this will give us n minus start. And so this is just the search time it took to do all of the searches. And then we're going to print out the results. We're going to get the title. And then this tells you, this is just a space maker basically. And then we're going to give the distance of the actual thing. Oh, okay, so that was very fast. And we'll see that the search term, the president speaks about the impact of renewable energy at the National Renewable Energy Lab. The first result is remarks by President Biden during a tour of the National Renewable Energy Lab, kind of what we're looking for. And then for the search term, the Vice President and the Prime Minister of Canada both speak. The first result is remarks by Vice President Harris and Prime Minister Trudeau of Canada before a bilateral meeting. So that's, you know, just showing that that's what we're looking for. And the search time was very, very low. And then at the end, you want to shut down your server so you can have it continue running. Default server dot stop. And that is it. That's how you create your own semantic text search application. And now I will take questions. Okay. Does this database allow to pre-filter on non-vector fields before executing the actual vector search? Date range, for example. Yes, yes, yes. So you can search with a filter, and I didn't demonstrate that here, but you can. I can show you some examples. There will probably be some links to find, but you can ping me after, and I can find the links for you. And we will, and basically, you know, you can pre-filter for, let's say, a specific type of date range or a specific location or something like that. So yes, it does allow that. QA.
And we had we had a question earlier in the session. I just want to capture that really quick. How do we measure the quality of some embeddings?
How do you measure the quality of some embeddings? That's a kind of broad question. I don't actually know how to. I don't know how to answer that. I don't know what that means. Usually, the quality of vector embeddings can be, you can use like the popularity of the model as a, you know, as a indicator. I'm not sure if that's exactly what you mean, but that's kind of the best that I can understand from what that means. Do you work with Llama Index, GPT Index, or LangChain? You know, that's a great question, because guess what? I have a couple of blog pieces that actually, the blog piece for Llama Index was just published this morning, I think. I think it was just published this morning. Emily, do you know where it is?
I do. I will get you that link in just 1 second.
Yes, that would be great. So yeah, we do. And in fact, if you come to the June one, you will see how to create a Q&A over a set of documents using Llama Index. So that is, so yes, we do. We do use Llama Index and LangChain, and I'll even show an example on how to use it. What's your opinion on Pinecone database? Can't say. Open source is the way to go. Let's see. What is there's a couple that what do you think of Google Universal Sentence Encoder? It's fine. It's good. You can use it. There's no like, I wouldn't say that there's any vector embedding like neural network or engine or whatever you want to call it that is necessarily better than any other. I mean, yes, there are some that are necessarily better. So for example, if you're using an RNN, like a very, very basic RNN that can not always accurately identify part of speech, you're probably better off using a different network to get your vector embeddings. But as long as you're using something that is able to, that is good enough in a sense to use, that is able to predict things pretty accurately, you're good. Okay, wait, I wanted to also address this, the linguistics one. I don't think that, I don't know like what you mean by familiar with linguistics, but like you should understand at least that like, there are some words that are similar to other words, and the quality of the output of your semantic text search is really decided by you. If you have a set of documents or it's decided by, I guess, like you, but also maybe like your users, right? The metric is kind of, it's quality, right? It's different from quantitative metrics. But in this case, we could show that we were able to find, the first result that we got back made sense. And as long as it makes sense to you or your users, that is a good indicator that you're getting, that, your index metric is fine, that your distance metric is fine, and that you are getting some set of results that are good. Is there anything else?
Which open source LLM do you prefer?
Which open source LLM do I prefer? Which open source LLM do I prefer? That's a good question. I don't really know. I don't have one that I would say is, specifically amazing. Maybe Claude. I don't know. It's the LLMs are all, at a certain level, the LLMs are all pretty similar. And like, my honest opinion is I'm not very satisfied with any of them right now.
We have a little bit of time left. Any additional questions that we've got for you, Jen, today? Drop them into the chat or into the Q&A panel. We'll give it just one more minute in case people are typing. Last call on questions. Thank you all for joining us. We hope you enjoyed the session. As I mentioned at the top of the hour, we will send out the recording to this. So if there's any section you need to review in more detail, you'll certainly have the opportunity to do that. And if you have any questions about where to find links to the documentation or any of the other materials that we referenced during the session, please just reply back to the email with the replay. We're happy to track stuff down for you.
Okay, I'm going to answer the last question from Ashish. Can you talk a little bit more about the nprobe argument? Yeah. Nprobe is basically how many of the clusters, in terms of IVF flat, is how many of the clusters you want to look at to look for the closest vectors. So the way the parallel search works is basically like, you have these different segments. They're all 512 megabytes. In our case, we definitely didn't have 512 megabytes data. We only had one segment. It goes to the nprobe. It says, okay, we're going to look into the 10 close centroids. And we're going to find the top 3 from each, and then I kind of unify them at the end. That's it. How do we decide best enlist and mprobe values for given data? Yeah, so these are more or less like, these are more or less kind of test and these are things that you test for. To be honest, it is mostly, so enlist is mostly going to be something that affects your the size of your index, and it affects the indexing speed, although indexing speed really isn't a problem with Milvus. So mainly the thing you're going to think about is size of your index, right? And then mprobe is going to be something that affects the latency of your search. And you can see that, that's really not a problem either, because we had our search in like 0.009 seconds. This is like less than this is like a millisecond basically, right? Or is that 10 milliseconds? It's less than, it's very, very quick. And so, you can kind of have mprobe go up, and as you get mprobe to go up, you'll probably have higher accuracy. But at a certain point, it's probably not worth having higher accuracy for higher latency. And then enlist, as you go up, it's going to take more memory, but you might be able to have better organized data. Can you recommend a model embedding for multilingual in Spanish? I'm sorry, I don't know anything that works in Spanish. Ashish says that the Cohere model is good for Spanish, I think. What is his workstation? Like, is it like this? What am I working with? I'm working on a MacBook Pro. This is like, I don't know, 2022, 2021. I don't even know which version this is. I'll just click here. I'm working with MacBook Pro on 12.5, 2021, 16 gigabytes of memory, and using the Apple M1 chip. But for reference, this also works on a 2013, 2014 Acer Aspire E, which is my Windows laptop that I have also played around with. But I totally recommend Macs in terms of programming. I just think they're nicer. Rather general way, do we have any metrics to decide which index we should use? For indexing, like which index you should use in terms of like, the IVF, HNSW, whether or not you want to use scalar quantization, product quantization, what you're looking at there is you're really looking at a set of trade-offs. And the set of trade-offs that you're looking at is the size of your index and the accuracy of your results, and latency when you do your query. But most cases, when you're creating the index, you're looking at size of the index and results. So quantizations like scalar quantization and product quantization make your index smaller, but they also make your accuracy lower. And then, HNSW is really good for accuracy, right? And it's even query speed is usually pretty good, assuming you don't get any like freak random numbers, but that makes your index size really big. A lot of people use HNSW now because it's cheap to buy memory, but it depends on what you're working with and what you need. Looks like most people's questions have been answered. Will quantum computers make things better for those dimensions? I also have no idea what this word here is, but okay. Will quantum computers make things better for those dimensions you just said? What dimensions? You mean like Can you clarify that? No, I'm not asking. No, I'm not asking you to clarify the word. Okay, okay, geeky. That makes sense. But I'm asking what you mean by what dimension. Like what dimensions are we talking about? Like the size of the index, or the number of embeddings? The size of the index. Okay, the size of the index. Will quantum computing make it better for the size of the index? I haven't given that much thought. I would say quantum computing will make your queries faster. That's I mean, in terms of like the size of the index, that's mainly memory. That's like your ROM, your RAM stuff. I would say quantum computing, as far as I know, kind of mostly affects your like speed of queries. And in terms of Milvus, yeah, it'll probably make it a little bit faster, but you can actually try like huge, like there's a reverse image search one as well. I did a reverse image search notebook, which I didn't send you the link, Emily, but I can find it. The reverse image search notebook is a lot like bigger of a data set, and it takes like 12 minutes or something to load the data. But even so, you can kind of like go through it and you can see that I'm going to send it here to, you can even see there that the time it takes is still incredibly small. It's like 60 milliseconds or something like that. Any other model you suggest other than OpenAI? Because OpenAI has a lot of limits right now in free version. What do you mean, like the LLMs? I would use. I mean, OpenAI, like the GPT model, is kind of like the default model for all the tools that are surrounding this ecosystem right now. But you could probably use like Bard or Palm or Claude, or there's another one that was released recently. I can't remember the name of. Yeah, I don't know. Those are kind of like the popular ones.
All right, we are just about at the end of the hour. We want to thank everyone for joining us today. Thank you for all the great questions. Eugen, thank you for putting on such a great session. We will see you all next time. If you want to see our calendar of upcoming webinars, including Eugen's next tutorial, which will be on June 15th, you can head over to zills.com/event, and we will catch you guys next time.
All right. Thanks, Emily. Thanks, everybody, for coming. I hope this was helpful.